Hi, my name is Bahadur Akhmedov. In this video lecture, we are going to discuss about the problem where we need to describe the null space of the following matrix. So let's say we're given a matrix which has one row and three columns. And what we need to do is we need to multiply this into another vector with the three rows in one column. So essentially it's going to have x1, x2, and x3. So that this is going to be equal to the 0. So, and the dimension of this vector is going to be 3 by 1. And if you multiply this T matrices, we're going to have simply a 0. So in order to find this x1 and x2, and in order to describe this, I would like to just write this down, the system of linear equations in this way. So x1 plus 2x2 plus 3x3 is equal to the 0. And what I want is I would like to solve this system of linear equations in two different ways. So by the way, I need to mention that, hey, so the system of linear equations is going to have infinitely many solutions. So the first thing which I would like to do is I would like to mention that, hey, I've got just one equation and three variables even. It means that one of the variables is the important one or dependent one, and the two other variables are the free variables. So essentially, I'm going to choose, let's say, x2 and x3 as the free variables, and x1 is going to be called as the pivot variable or dependent variable. So what I do is I essentially am going to introduce the two parameters because I've got two free variables. So x2 is going to be the first parameter, so the t1, let's say, and x3 is going to be the second parameter. x3 is going to be equal to the second parameter, and I'm going to just substitute the first parameter and the second parameter with the x2 and x3 in this equation. It is going to be x1 is equal to the 2, oh sorry, minus 2, because these two terms are going to go to the right, and it's going to be minus 2t1 minus 3t2. I'm just substituting t1 was the x2 and t2 was the x3. Okay, so instead of just having one system, one equation, I've just got three equations. And again, I would like to write this down that the x bar is going to have the components, three components, x1, x2, and x3. So this is what I'm looking for. And x1 is going to be equal to the minus 2t1 minus 3t2. x2 is going to be equal to the t1, and x3 is equal to the t2. So now what I want is I would like to just separate the terms for the t1 and t2. So this is going to be a minus 2t1 t1 and 0, and this should be added to the minus 3t2 0 t2. So you see, so I've separated all the terms with the t1 and all the terms with the t2, and the reason is so and I can easily check whether this is true by just summing them, right? So this is all about t1, this is all about t2. If you sum these two columns, you're going to get essentially this column. So now what we do is we are going to write down the solution or the null space by taking out the t1 from the brackets. It's going to be minus 2, 1, 0 times to the t1 plus if you take out the t2 from the brackets, it's going to be minus 3, 0, and 1 times to the t2. So you see, so the solution or the null space of this matrix, or the solution for this homogeneous system of linear equations ax is equal to the 0, is going to be all possible linear combinations of these two vectors, right? Because you're multiplying one vector to the constant, another vector to the constant, where t1 and t2 are any constants. And these two vectors, which are essentially explaining us the null space, are going to be called as the spatial solutions. So this vector and this vector are going to be called as the spatial solutions. And it appears you can get the spatial solutions, right, without introducing the parameters as we did before. So our ultimate goal is, why don't we just generate the spatial solutions and write down the null space, right, and immediately as the linear combinations of the spatial solutions instead of introduce the parameters and solve the system of linear equations. Okay, the idea would be like this. So I'm going to write down again the system of linear equations. In this case, it is going to be just one equation. x1 plus 2x2 plus 3x3 is equal to the 0. Okay? And again, first of all, what I have to do is I need to identify which of the variables are the free variables and which of them are the pivot variables. So these two variables are going to be considered as the free variables. And again, you can choose the free variables as any two variables. Okay? So here we're just choosing this free x2 and x3 as a free variable just because of the convention. So we are going to discuss why exactly x2 and x3 are the free variables in a moment. Later on, so let's say x1 is going to be the pivot variable. Okay. And what we have to do now is, this is going to be the most strange case. So the number of the free variables is going to tell me the number of these spatial solutions. Spatial solutions. And how do I find the spatial solutions? You see, so the spatial solutions are the three-dimensional vectors, right? And how do I find the spatial solutions? Is that I'm just going to assign x2 and x3 to be equal to the 1 and 0. If I just assign this and substitute this to this equation, which is given here, I can find x1 from here, right? So it's going to be x1 is equal to the minus 2x2 minus 3x3, which is going to be equal to the minus 2, right? So I've got now the vector. So was the x1 to be equal to the minus 2, was the x2 to be equal to the 1, and x3 is equal to the 0. So I'm going to call this as the spatial solution 1, right? At the same time, the number of the free variables, which is equal to the 2 in this case, is going to tell me that, hey, there exists another spatial solution as well. And can you guess how we can find this? So in the first case, in order to find the spatial solutions, we set x2 to be equal to the 1 and x3 to be equal to the 0. In the second case, obviously, x2 should be equal to the 0 and x3 is equal to the 1. And we have to substitute this to this equation of the x1 is equal to the minus 2x2 minus 3x3. In this case, it's going to be equal to the minus 3x3. Then I'm going to construct the spatial solution 2 by just copy the value of the x1. So sorry, it's going to be simply minus x3, right? Because x3 is equal to the 1. So the x1 is going to be equal to the minus 3, x2 is equal to the 0, and x3 is equal to the 1. And this is going to be the second spatial solutions. And what I have to do is I can describe the null space as the linear combinations of the spatial solutions. So essentially S1 is going to be multiplied to the T1 plus S2 is going to be multiplied to the T2. Or essentially we can write this as a minus 2, 1, and 0 times the T1 plus minus 3, 0, and 1 is going to be multiplied to the T2, which is going to be all vectors from the null space of this matrix A. And if you would just compare the solution which we got before and this solution, so you will see that they are the same. So this solution and this solution are the same. So you see, we can construct the null space of the matrix by solving a homogeneous system of linear equations, right? And if you have the infinite many solutions, you can write down all of these infinite many solutions in the parametric form, and we can derive this parametric equation which describes the null space in two different ways. So later on, we're going to use always this method because it can be generalized to the high dimensional matrices and high dimensional null spaces very much easily. So thank you very much for your attention. I hope that this video was helpful for you.